Today we're starting chapter 6. Chapter 6 is all about polynomial equations and things, so today we're just starting with some exponential properties. So we'll just be in section 6.1 today with properties of exponents, things you guys have talked about before, so we're just going to do kind of a brief and quick overview of some of these and using some of these properties. So first off with negative exponents. For any real number a not equal to 0 and some integer n, if a is raised to the negative n power, what that really means is you're writing the reciprocal of that number. So you're writing 1 over a to the n. Notice the a to the n goes positive at that point because now it's in the denominator. It's gone back to positive exponents. However, if it starts as negative in the denominator, then it goes to the numerator and becomes positive. So whenever you switch places with it, it becomes positive. You lose the negative. This is not the same as saying a times negative n. The a is not negative, just the exponent is negative. The number itself is not negative. So 2 to the negative 3, for example, these aren't on your paper, don't worry about them, but 2 to the negative 3 would really be saying 1 over 2 cubed, which is 1 over 8. Same thing for 1 over b to the negative 8. You could rewrite that as b to the positive 8, just by switching it, now it's over 1 instead. So that's all that's happening there, is just you reversing and flip-flopping where those variables, or where those terms, are falling. Alright, let's go ahead and take a look at an example of this. So if we look at these two examples, we're going to go through some of these properties more and how to use this, but I do want to show you these. So we're simplifying. When we multiply, so we have 3 times a negative 4 gives us a negative 12. Then we have x cubed times x squared. Remember, when you multiply like bases, you add the exponent. So we get x to the 5th. Y squared times y to the 4th will give us y to the 6th. So notice here we had no negative exponents. The negatives out front multiplied together just like normal negative integers. The next one is a little different because we have negative exponents. So for this one, we're going to multiply all of our like terms. So we have a to the negative 3 times a squared. We add them. So we have a to the negative 1. b to the 4th stays the same because there's nothing to multiply by. And same thing for c to the negative 1. Now you never want to leave it with a negative exponent. That's not simplified. You do want to rewrite it or reduce it. So b to the 4th stays where it is. It doesn't change because it doesn't have a negative. So it stays. The other two go to the bottom. So we have a to the 1st times c to the 1st. So only those with the negative exponent are going to move to the denominator, not the whole thing. So just because one of them has it doesn't mean all of them have it. It's just the ones with the negative exponents. The b stayed on top. Alright, we're going to go ahead and take a look at some some properties of powers now. The first one being the product of powers. So this is kind of what we just saw. If you're multiplying two things with the same base, you add the exponents. So a to the m times a to the n, you add m plus n. So for the example that I have written there, 4 squared times 4 to the 9th, you multiply those and you get 4 to the 2 plus 9, or 11th. 4 to the 11th power. And again, those are on your sheet. If you want to write those in just for examples for yourself, you're welcome to. But I put them up there just so you guys can kind of see an example of what we're doing. The next one is a quotient of powers. Well, if we add when we multiply, we're going to subtract when we divide. So when you divide like bases, you subtract the exponent. So 5 cubed divided by 5. Remember that something with no exponent is really having an exponent of 1. So 3 minus 1 gives us 5 squared. So you subtract those, and then 5 squared would be equal to 25. And then I'm going to go ahead and group the rest of these all into one slide. So we have a and b are just some real numbers, and m and n are integers. So the power of a power, you're going to multiply. So if you have a squared to the 3rd, you'd multiply 2 times 3. So here we have a to the m to the n, so you multiply m times n. The power of a product, so you're kind of reversing that. If you have two things being multiplied on the inside and a product on the outside, or an exponent on the outside, you distribute that exponent. That's only when you're multiplying. You cannot do that when you're adding. So if I have a plus b to the m, that is not equal to a to the m plus b to the m. That's not the same. You can't do that. So you can do it when you're multiplying and dividing, so that's here. And then the zero product, anything to the zero power is 1. Doesn't matter what it is or how many things there are, anything to the zero power is 1. So let's go through and do some examples of this. So p to the third over p to the eighth. So we're subtracting because we are dividing. So we're dividing these two, so I go p to the third over p to the eighth. 3 minus 8 gives me p to the negative 5. However, I can't leave it as a negative exponent, so I'm going to rewrite that as 1 over p to the fifth. So again, we want to divide because we have y to the 12th over y to the 4th. So 12 minus 4 gives me y to the 8th. It's positive, we can leave it as is. That's all the further we have to go. And then we have, now here, these divide just like normal. You're not subtracting them. They're integers. You have to divide them just like normal. So 15 divided by negative 3 is a negative 5. C to the fifth divided by c to the second. Subtract 5 minus 2, we get c cubed. D to the third over d to the seventh. 3 minus 7 is d to the negative fourth. So then negative 5, again, it's a negative 5. Do not move it to the denominator. Having a negative integer is different than a negative exponent. So we have negative 5c cubed, and then d to the fourth moves to the denominator. Negative 5c cubed over d to the fourth. Now these examples kind of use some of those other properties that we grouped together, that second set of them. So let's take a look at these. So here we have a power to a power, so a cubed to the sixth. We multiply 3 times 6, so we end up getting a to the 18th power. And again, we have this to the fourth, so since we're dividing, I can distribute that. It distributes to everything on the inside, to the 3, to the x, and to the y. So I'm going to carry this negative up to the 3. So we'd have negative 3 to the fourth, x to the fourth, over y to the fourth. And negative 3 to the fourth is going to give me a positive 81, so I end up with 81x to the fourth all over y to the fourth. And that's it. That's where it stops. Again, we distribute the fifth to everything on the inside. So I'm going to have negative 2 to the fifth. I'm going to have p cubed to the fifth times s squared to the fifth. So negative 2 to the fifth is going to give me a negative 32. P to the third to the fifth, we multiply, so we get p to the 15th. And then s squared to the fifth gives me s to the 10th. Now when you have a negative on the outside, you can kind of do this a couple of different ways. You could take care of the negative first, or you could just distribute it and then take care of it. So I'm going to go ahead and distribute it first. So we're going to end up with a to the negative 3 over 4 to the negative 3. Now they're both negative, so essentially I'm just going to flip them. So then we have 4 to the third all over a to the third. And then 4 to the third is 64 over a cubed. So there, which is kind of an example of the power to a power and distributing that, or the power of a quotient. And again, this one at the bottom, you could have flipped them first. So I could have said, okay, this is going to be 4 over a. Then it's cubed. And then I would have ended up with the same thing that I did. Either way would give you the same answer. One more example of this, then I'll jump to a couple of other things here. So here's a bigger one. So we are going to distribute that 4 to everything on the inside. So here again, you want to make sure that you're getting everything. However, notice we have some duplicate things on the inside, so I'm going to go ahead and reduce those first before I distribute that one. So we're still going to leave negative. We're going to have 2 x to the 3n divided by x to the 2n. 3n minus 2n is just x to the n. And then we're going to leave that with y to the third. This is all raised to the 4th power. Now I can distribute that 4. So we'll have negative 2 to the 4th times x to the n to the 4th all over y to the third to the 4th. So negative 2 to the 4th gives me 16. X to the 4n all over y to the 12th. So again, you can reduce and simplify inside first before you distribute this, or it could have distributed it all first and then subtracted. Either way, again, you get the same answer. Standard notation and scientific notation. This is something you guys may have covered or started to cover or already covered in science classes. Standard notation is just, that's the way we express numbers. That's the way we've always done it, that's the way we always will. Scientific notation is when you take that number that's really big or really small and you write it as an integer times 10 to some power. So it could be like 1.5 times 10 to the 6th power. Would represent a really big number. So just as an example, we're going to kind of take a look at an example here of using that in an actual word problem here. So after the Sun, the next closest star to Earth is Alpha Centauri C, which is about 4 times 10 to the 16th meters away. So that means you have 4 and you're adding 16 zeros to it. How long does it take light from Alpha Centauri C to reach Earth? Light travels at a speed of about 3.0 times 10 to the 8th meters per second. So what we want to do here is we're kind of looking at that distance equals rate times time, but we're asking about time because we know the rate and we know the distance. So I'm going to divide by r and we're going to rearrange this so we have time is equal to distance divided by rate. Well, for us, the distance is 4 times 10 to the 16th divided by 3 times 10 to the 8th. Well, I can separate this so that I end up with 4 over 3 times, and then we're going to use exponent rules because we're going to have 10 to the 16th all over 10 to the 8th. So even though it's not a variable, we're still using the same rules for exponents. So 10 to the 16th over 10 to the 8th, we subtract 16 over 8, so we get 4 thirds, which will be approximately 1.3 times 10 to the 8 seconds. So that's just a practical example of when you might use these exponent rules with scientific things. And a lot of times these exponent rules are with scientific things when you're dealing with speeds like this or really small atoms or things like that. Alright, and your homework tonight is 11 through 22 and 27 and 28 on page 316.